we're looking at the idea of conservation of linear momentum. So first thing first, what is linear momentum? I'll give you guys two scenarios to recall. Say you have a deflating balloon flying around and coming towards you guys, and with the same velocity you have a heavier object coming towards you guys. So now, which is more scarier? Which is more scarier? Scenario 2, right? So this will be more scarier. Do you guys agree? Why? Why is this more scarier when you have a balloon moving at the same velocity, 10 meter per second, and you have a mass which is also moving at same velocity? Of course, this is heavier object compared to this. Yes, and the answer lies in the fact that this is heavier. But what if we have the same object, moving slowly towards you guys, rolling towards you guys? The same object, it is coming faster though. So which is more scary? Scenario 2. But both have the same mass. So even though both have the same mass, the velocity are different. So it is that it has more velocity, it makes it scary. A simple example is a bullet. Right? Bullet just sitting next to you or kept next to you is not scary, but when it gains that velocity, that's when it can hurt you bad. You guys agree? So that is this, to take all of this into account, or to talk about this oopness, the IO factor, right? The sudden jerk or not that sudden hit. If you guys do MMA or do some kind of boxing, kickboxing, or any kind of martial arts and stuff, actually not martial art, but anything wherein you guys get punched, you understand this factor, right? Linear momentum plays a very big role in all of this. This oopness, this IO factor is your linear momentum. So now we are looking at conservation of linear. Conservation means what? Conservation means it's saved. What is it saved? What is saved over here? Let's look at it. The total amount of IO factor in the universe is always the same. The before and after IO factor will remain the same if system is left alone. So let me put it more officially. If and only if the total external force acting on a system is 0, then the total moment of the system is a constant vector. Okay, I'll give you guys an example. I have a bunch of objects, they are moving. Okay, so this is a closed box. You can imagine that it's a carrom board without the holes, right? There's no place wherein the pawns can go, and the surface is very smooth. It almost has no friction at all. Let's take an ideal scenario. It has no friction. So what happens? Let's see. Observe any one you observe, you will get to see a lot of interaction. Okay. So what the theorem tells is, when you have such a system wherein there's no external force acting each other. See, there's no one pushing them around other than the pawn themselves, other than the striker or whatever this is, ball or whatever you want to imagine, air particles, gas particles, or many scenarios actually. So if you can imagine this, then given the system, there's no one acting on it, no one pushing around anything over here. If I add up any velocity and mass, respective mass, in any point of time, the product, the sum, the product and then the sum will remain the same. Mass into velocity here of all of this will be same as mass into velocity of all of this. the total momentum each second will remain the same. Okay, so the total momentum will remain the same. The product, basically, you take the product of this product of this vector product, that is, vector form. You have your I component, j component, and so on and so forth. So each of this, you multiply that with the mass, add them up, it will remain the same. Okay, so that will remain the same. So what is the point of this? Guys, I can promise you, it will make a lot of problems very simple. Problems which were very difficult to solve till now, they look very simple from now. And you will be able to understand as complex thing as rocket launches. Okay, so let's start with few derivations, then go on to numericals, and you will understand the concept better. For now, you guys have to copy all of this.